Hi everyone! Today we're going to be going over the basics of kinematics in one dimension. So the first thing that we're going to do is define two important topics that are used in physics quite a bit: vectors and scalar. So, a vector is any quantity with both magnitude and direction. For example, if I say that this boy is running at 3 miles per hour to the east, that is a vector because I have both magnitude and direction. Vectors can be represented using arrows or plus or minuses to indicate direction and magnitude. We will go more into depth about adding, dividing, multiplying vectors in another video. Next, scalar is basically just a quantity with no direction. So the scalar version of the example that I just gave would be that this boy is running at 3 miles per hour. As you can see, I have not given any direction, and I have just given the magnitude. So that is what vector and scalar is and how they differentiate. So now we're going to go over position. Position is where an object is at a particular time relative to a convenient reference frame. For example, the Earth can be a reference plane, or a person inside an airplane, and the airplane can be the relative reference plane of the person. In this case, I'm going to use familiar Earth as our reference frame. Let's say that I have a car who's traveling on a flat landscape, because right now we're in one dimension, and I assume where it starts at is position 0. This car begins to travel at a certain speed and passes through these positions until it runs out of gas. Let's say that our car is traveling, and right here at position 5, it runs out of gas. We see that on the car's internal timer, let's say, the time is 30 seconds. That means starting from position 0, and let's assume time 0, our car traveled to position 5 in about 30 seconds. And because we're using Earth as our relative reference frame, we can see that from position 0, the car is now at position 5. Lots of times, graphing position is very useful in physics problems. As you know, graphing Cartesian requires an x and y point. In the case of position, our x-coordinate is our time, and our y-coordinate is our position. Time is often represented in seconds, and position, which is actually often represented with x, is usually in meters. Now we're going to go over two commonly mistaken and mixed up vectors and scalars, known as distance and displacement. Because distance and displacement sound very similar to an introductory course, it's often one of the biggest mistakes of students. So I'm going to define to you what distance is. Distance is the magnitude or the size of the traveled displacement between two positions. So for example, if I have a car, very badly drawn, that starts right here at position 0 and travels on a curvy, loopy road and ends right back at its original position, The distance traveled is the total distance of this road. Let's say that this road is 30 miles. That means the distance that this car has traveled is 30 miles. Now, where it gets confusing for some people is the concept of displacement. Displacement is actually the object's change in position. So, if the car started at position 0 and traveled this entire loopy road and ended right back where it started, so again, position 0, its displacement is 0. Displacement is represented with delta x, and it's found using the final position minus the initial position. And that shows us that displacement is a vector quantity and distance is a scalar quantity. Displacement, once again, you can see is final position minus initial position, telling us the change between these two positions of the car. So another example would be if I had my car start at position 5, let's say, and it traveled this loopy road and went right back here to position 8. We can calculate displacement by saying final position, which is 8, minus the initial position, which is 5, is 3. That tells us that the car's displacement is 3. And let's once again assume that this loopy road is 30 miles. That means that the distance the car traveled is 30 miles, and the displacement it had is 3. 3 miles, I mean. And this can tell us that distance traveled can actually sometimes, or sometimes even most of the time, be greater than the magnitude of its displacement. A more tough example is negative displacement. If our car starts at position 5, it travels a 30-mile road and ends right here behind its original position. Considering it's behind position 5, we can say that this is position 0. Calculating its displacement, we have our final position as 0 minus our initial position, which is 5, and that tells us that our displacement is negative 5 miles. Usually distance and displacement are in meters, but in this case, since I started off with miles, I'm keeping that consistent. Another commonly mistaken vector versus scalar quantity is velocity versus speed. So velocity is the measure of displacement over the change in time. This is referred to as average velocity. Because we know that displacement is a vector, we can guess that velocity is going to be our vector quantity. Velocity is represented with a v with a vector symbol, and its SI unit is meters per second. For example, going back to that car analogy, if I start at position 0 and ended at position 5, and the time that it took our car to travel this displacement, was 30 seconds, we can calculate our average velocity by using the equation displacement, which in this case is 5 meters, considering that our units on this number line is meters, divided by our change in time, assuming that at position 0, our initial time is 0, which is 30 seconds, giving us an average velocity of 1/6 meters per second. And again, velocity is a vector, so it can be represented with a positive negative sign. In this case, in physics, right is positive and left is negative. So in this case, our velocity is going to be positive 1/6 meters per second. Or if we used north, east, southwest, our car is traveling east, so we can say our car is traveling at 1/6 meters per second east. Next, we have speed. Speed can be distance traveled by elapsed time, and that means that average speed can be greater than velocity in some cases because we saw that distance is sometimes greater than displacement. In most cases where velocity is represented and speed is also represented, our velocity's magnitude and our speed are equivalent. However, because speed is actually the measure of distance over time, average speed can sometimes differ from velocity in certain cases. So in this case, where a car displaced from position 0 to position 5, assuming our number line is in meters, and at position 0 we have 0 seconds, our car travels at an unknown speed, 5 meters, because that is our distance, which is equivalent to our displacement. This takes an elapsed time of 30 seconds. So our speed is, once again, 5/30 meters over seconds, which equals to 1/6 meters per second. As you can see, this is very similar to velocity, and the only thing is that we don't indicate the direction of our car. So sometimes we can say that our car is traveling left, up, down, this exact speed, but our velocity can be different because the direction of our car traveling is different. Acceleration is a vector quantity that occurs when velocity changes magnitude or direction. And this is very important because many people assume that acceleration is speeding up. However, acceleration, once again, is changes in magnitude of velocity or changes in direction of velocity. So, for example, if our car is speeding up, we would say it's accelerating. If it's slowing down, we will say it's accelerating. If the car is switching directions by turning left, turning right, going up, down, any change in its direction, despite its speed staying the same, we would say that it's accelerating. Average acceleration is represented with delta v over elapsed time, or delta t. Delta basically represents final minus initial, or a change between 2 points of velocity, position, etc. So we can calculate delta v using v final minus v initial, or sometimes vi, over delta t, which is our t final minus our t initial. This gives us our average velocity. And because we know that velocity is also a vector, we know that acceleration is also a vector. And the reason that changes in direction can give us acceleration is because velocity can change based on its direction because we know that it's a vector. For example, in physics, once again, left is defined as negative and right is defined as positive unless otherwise specified. So if our velocity is 50 meters per second to the right, which is positive initially, and finally at its final time, it's traveling at the same speed, 50 meters per second, but left, which is negative, that tells us that we have a change in direction. However, not a change in our magnitude. And that still gives us a positive for the absolute value of our delta V, which means that we have an acceleration. Later on in future videos, we will determine how acceleration can occur and how it can change. Lastly, we're going to go over the one-dimensional kinematic equations. So something really important to remember is that these equations can only be used for constant acceleration. This was a common mistake that I made a lot in introduction physics classes, where I would use kinematic equations for constant acceleration, where the acceleration of the problem was not constant. So you have to remember that all of these equations I'm going to give you are for constant accelerations. So kinematic equations are used to determine the velocity of an object, the time elapsed of an object traveling at a certain speed or through a certain change in position, the displacement of that object, or its acceleration. These four quantities can be unknown, and you can use the other quantities that are known to figure out the unknown quantity. These four equations are: our final velocity equals to initial velocity plus constant acceleration times elapsed time. Next, we have displacement, which we know as final position minus initial position, equals to initial velocity times elapsed time plus 1/2 of our acceleration times elapsed time squared. Next, we have our final velocity squared equals to initial velocity squared plus 2 times our acceleration times our displacement. And lastly, our final kinematic equation is our displacement, our change in position, is equal to 1/2 initial velocity plus final velocity times our elapsed time. These four equations can be used to solve for initial velocity, acceleration, elapsed time, and displacement. And sometimes breaking apart displacement as final minus initial, we can specifically solve for the final position and the initial position if we have the information. The reason that I also wrote the time as delta t is because sometimes you need to be careful and remember that time initial does not always start at 0 seconds. So that is something you also need to pay attention. Now I'm going to go over some practice problems using these equations. And if you want to stick around, you may, or if you have your own practice, you may also do that as well. So now we're going to go over a simple first equation using our kinematic equations. So an object is traveling at a constant velocity of 15 meters per second when it experiences a constant acceleration of 3.5 meters per second squared for an elapsed time of 11 seconds. What is its final velocity after acceleration? So the best thing to do in these kinds of equations that I have found to be very helpful is using a known and unknown chart. Sorry, my line isn't very straight. So first we're going to see what we know in our equation. We know that our object is traveling at a constant velocity of 15 meters per second. And that's before any acceleration is applied to it. So we're going to assume that our initial velocity is 15 meters per second. We're given an acceleration of 3.5 meters per second squared, and because it doesn't indicate any negative, we're going to assume that that is in the right direction. And it also gives us a elapsed time of 11 seconds. Our unknown is our final velocity and also our delta x. So we have to use one of these four equations in order to find our final velocity without using delta x. So it looks like our first equation is our best option because we use v final, which is our unknown, equals to v initial plus acceleration times elapsed time. So plugging these in, we're going to have v final equals to our initial velocity of 15 meters per second plus an acceleration of 3.5 meters per second squared times an elapsed time of 11 seconds. Using my calculator, I'm going to multiply acceleration and time. And by the way, these are incorrect SI units, meters and seconds. If these were, for example, inches or feet, hours, or minutes, you would likely need to convert them to meters and seconds. So the acceleration times elapsed time is 38.5. We're going to add 15 to this, and we're going to have our final velocity be equal to 53.5 meters per second. Our next problem says, an object is traveling at an initial velocity of 52 meters per second and experiences an acceleration of negative 9.8 meters per second squared. How much time will it take until the object comes to rest? So once again, we're going to make a known-unknown chart. Even though right now a known-unknown chart seems unnecessary, once problems start to get more complicated, it's actually very useful because I was also a first-time doubter about using this. So we're given that our initial velocity is 52 meters per second. Our acceleration is negative 9.8 meters per second squared. And our unknown is delta t, delta x, or our displacement. And actually, right here when it says until the object comes to rest, rest means that your velocity is 0 meters per second. So we actually know our final velocity is 0 meters per second. So we're going to need to have an equation that lets us find the time without using delta x. So again, we see that the very first equation, v final equals to v initial plus acceleration times elapsed time, is going to be the best for this problem. So we know our v final is going to be 0 meters per second because that is what it wants. It wants the object to come to rest. Our initial velocity is 52 meters per second plus a acceleration of negative 9.8 meters per second squared times an unknown elapsed time. So now we're going to manipulate this equation algebraically to isolate delta t. So we know that 0 minus 52 is going to give us negative 52 meters per second, and this is going to be equal to negative 9.8 meters per second squared times delta t. And now we're solving or isolating delta t, so we're going to divide our acceleration from both sides, and we're going to have negative 52 meters per second divided by negative 9.8 meters per second squared, which is equal to our delta t. And using a calculator, we see that our elapsed time is equal to 5.306, or about 5.31 seconds. So this is going to be a challenge problem in our last practice question, which uses the concept of a free fall. A free fall is basically when an object is given an initial velocity and thrown up into the air on Earth, or let go from an initial height on Earth. The reason we know this is that we can solve these problems, is because we know the constant acceleration of Earth as 9.8 meters per second squared. In some cases where physicists define up as positive and down as negative, and because if you're standing flat on an area of Earth, acceleration of the Earth or its gravity will pull down. So sometimes g will be defined as negative acceleration. Next, we have to know something important in free fall, and this won't be used in this particular problem, but it's going to be helpful information for some more complex problems where you may not know what to do. And this is where if I throw an object straight up or let it fall down from a high point, at some height or some time, our object is going to have a zero velocity before accelerating and becoming a negative velocity. So for example, if my initial velocity is 10 meters per second, throwing up, my ball travels, decreases in velocity. The reason for this is because acceleration pulls down, so opposite of the direction of my initial velocity. So I will reach zero velocity at some height and time, and right after that, my velocity starts becoming more and more negative, again due to the acceleration being opposite to the direction of my velocity, or down or negative. So there's many ways to represent direction. So in this problem, we're not going to be using this concept of having a zero velocity at a certain time, but once again, I'm going to add some extra practice problems below in the linked in the description that may need you to use this concept. So for this question, it says that a ball is thrown upward straight from the ground with an initial velocity of 120 meters per second. How high will the object be after 4 seconds? So using our known and unknown chart again, we know that our initial velocity is positive 120 meters per second. Because this is a free fall on Earth, we know that our acceleration is negative 9.8 meters per second squared, and our elapsed time is 4 seconds. The question wants us to find out how high our object will be. In this case, we can use delta x or delta y. Some people use delta y because this is in the vertical direction. It's still in one dimension though, because we're not using both horizontal and vertical simultaneously. So we don't know our displacement and we don't know our final velocity. So we need to use an equation without final velocity in order to figure out our displacement. So it looks like using our second equation is going to be the best. Our second equation tells us that displacement is equal to our initial velocity times our elapsed time plus 1/2 our acceleration times elapsed time squared. This already has our displacement isolated, so all we have to do is plug in 120 meters per second as our initial velocity multiplied by 4 seconds plus 1/2. And remember that because we're throwing upward and that is considered positive in this equation, we're going to be using negative 9.8 meters per second squared as our acceleration. And our elapsed time again is 4 seconds, and that is squared. So plugging this into our calculator, a 120 times 4 is going to be 480 plus 1/2 times negative 9.8 times 4 squared, which is 16, is going to give us a displacement of 401.6 meters. And that means that if we assume that the bottom, or where we first threw our ball, as 0 meters, at 4 seconds, our displacement is 401.6 meters, and that means that its position at 4 seconds is 401.6 meters above the ground.